Welcome to Process Control lecture series. In my previous lecture, I completed chapter number 8. That means in that lecture we discussed about the feedback control system, feed forward control system, ratio control system. Then after we discussed about the cascade control system and the water level control system. That means inside the drum water level control system, and swelling, swinging effect and inverse response. Now we start new chapter, chapter number 6. And in this lecture we discuss about the first one topic. This is the velocity and position algorithm of PID control. And then we discuss about the Bumpless Transfer. So now we start with the first one topic, that is the velocity and position algorithm of PID control. In the digital control mode, the error signal is first sampled and control output is computed numerically through a digital process. So now the controller output for a continuous type PID controller is ut is equals to kp et plus 1 upon tau I integration e tau, or we can say t, dt plus td det by dt. So this equation is represent the discrete form of this continuous PID controller. That means up to now we discussed about the continuous process of the PID controller. Now here we start a discussion about the discrete process. So this equation indicates the discrete approach of the PID controller. The above equation can be discretized at a small sampling interval t0 as shown in figure. So here we can see this is the graph of the error. This et is indicate the error signal, and we divide into the time interval plot, that is t0, t1, t2 accordingly. Here kp is represent the gain and et is indicated the error signal. Now taking the first order derivation of the last equation, taking the first order derivation from this figure, so we can write that dE by dt is equals to 1 upon t0 ek minus 1. Same as, and using a rectangular integration, we can approximate as 0 to t integration et dt is equals to t0 summation I is equals to 0 to ki ei t is equals to k into t. So here instead of integration we just divide into the summation form. So we can write 0 to ki. So now we replace the derivative and integral term in the equation number 1. So we obtain ut is equals to kp ek plus t0 ti summation k is equals to I is equals to 0 to I ei plus td upon t0 ek minus 1. So now just we replace the derivation and integration term in the last equation. So we get here this equation. Now this is our equation, and we give is a equation number 2. The above algorithm is known as position algorithm. That means this equation represents the position algorithm. But the major problem here is that the error value at all the time instant are to be stored. That means at at least the second term of the RHS of the equation number 2 at each instant have to be stored. So this is the main problem of this position algorithm or this equation we can say. An alternative approach is known as velocity algorithm and can be obtained by following. That means now we start a procedure to get the velocity algorithm. So we have the position algorithm equation. This is now we start a procedure to get the velocity form. So here from this equation number 2, one can return the error signal at k minus 1 term instant as u k minus 1 kp e k minus 1 t0 ti summation k I equals to 0 to k equals to 2 ei plus td t0 e k minus 1 minus e k minus 1. Just we replace, instead of k, we write here the k minus 1. So we get this equation. Now we subtracting the equation number 3 from the equation number 2. So we get this equation as, that means uk minus 1. So we can write as a delta uk. And the difference of this equation we can write as a kp is the common and ek minus 1, that is first term. Now integration term we can write as a t0 upon ti ek minus 1 plus td upon t0 ek minus 2 ek minus 1 plus ek minus 2. So we can write this equation in a simple form as q0 ek plus qi ek minus 1 plus q2 ek minus 2. So this is the velocity form of this equation, and here this q0 is indicate the kp into 1 plus td upon t0, same as q1 indicate the kp 1 plus 2 td upon t0 minus t0 upon ti, and q2 indicate the kp td upon t0. So the above algorithm is known as velocity algorithm. The major advantage of this algorithm is that it is of recursive type. That means this is a recursive type algorithm. It calculates the incremental output at each sample instant. As the result, it requires only to store 3 previous values. That means only require 3 previous values, which is that ek, ek minus 1 and ek minus 2. So this is the advantage of this algorithm, that is velocity algorithm. So we discuss here the position and velocity algorithm. Now we discuss about the next one is the Bumpless Transfer. So first of all, question come in our mind, what is Bumpless Transport? So after reading name, you can understand. Bumpless, you have seen bump on the road, and bumpless road you can also see. So same as here we discuss about. Now we understand in terms of the controller. Bumpless transfer is the method by which a controller can be transited from manual mode to automatic mode. That means we can transfer the controller from the manual mode to automatic mode without disturbing the process. So it's known as bumpless transfer. Its aim is to keep the controller output the same when switching automatic to manual. That is, if the controller is at 50% output in the automatic mode, it should retain that 50% output as you switch it to the manual. If you switch from manual to automatic, the same should apply. That means when what? If the controller output is 50% at automatic mode and we shift the process into the manual mode, then it indicates same 50% output. So this is known as Bumpless Transfer. Most modern PID controllers have Bumpless Transfer built in, including PLC and DCS PID controller. So we discussed about the more detail of the Bumpless Transfer by using this example. So here in this figure you can see at the 10 AM the operator placed a temperature controller loop in the manual. So you can see this is the first line. This is at the 10 AM the operator is transformed automatic to manual. The set point is 280 Fahrenheit at the time of this transition. The operator decides to manually decrease the controller valve position from 40% to 30%. So here the operator is changing the valve position from 40% to 30%. Here you can see this is a SP is indicators point our desired value set point. So this line indicates set point. Then this is the PV, that is the process volume available, and this red line indicates the controller output. So here you can see after the 10 AM the controller output is decreased because the operator is changed from the 40% to 30%. Now what happened we discussed. The process variable after several minutes settle out at 220 Fahrenheit. At 11 AM the operator decides to switch the loop back in the automatic mode. At that time, set point is 280 Fahrenheit and the process variable is 220 Fahrenheit. So this is the big difference between these two, SP and PV. So as soon as operator flips, that means change from the manual to automatic, the switch, the control valve goes to 100% open because to reduce the deviation from 30%. Alarm starts going off, level and pressure starts swinging, and in general everyone associated with the operating the plant gets very upset. So here this is the example to understand what is the importance of Bumpless Transfer in the industry. So the remedy here is quite straightforward. The control logic should be decided to inform the PID controller when the loop has been placed in a manual mode, or second one is have the PID controller track the valve of value of the controller value position that is being established by the plant operator. So we can control more effectively. By having the PID controller track the actual valve position, we will prevent it from the winding up to either the completely closed or completely open position. Proportional bump and the time of the transfer from manual to automatic. So here we understand Bumpless Transfer by using the operation of the proportional controller. So assume that we did our job and properly design a PID tracking system that prevent the PID controller from winding up when the control loop was in manual. So let's take a look at what could happen in our previous example. At 10 AM, the operator placed a temperature control loop in manual. Okay, already we know. As above, SP is equals to 280 Fahrenheit. At the time of this transition, the operator decides to manually decrease the control valve position from 40% to 30%. the PV after several minutes settle out at 220°F. At 11 am, the operator decides to switch the loop back in the automatic mode. Now, at that time, SP is equals to 280°F and PV is equals to 220°F. So as soon as operator flips the switch, the control valve goes to 50% off point from 30%. Alarm may still trigger and disturbance to the process may still occur. Maybe not quite as bad as without tracking, but still very disruptive. So what happened? So not in the above example that at the time that the switch from manual to automatic occurred, there was an error represent SP minus PV is equals to 60°F, because we know there is a large difference. So even though we had the PID controller tracking the position of the control valve, the first time it calculated a control valve position, the proportional term of the PID controller would bump due to the presence of the error. The position expect is that the bump was less than the which occurred without the PID track, but there was a substantial bump nonetheless. So now what should we do? Well, there was two options to control this bump. So which are that? So first one is design the set point to track the PV when the control loop is placed in the menu. Now we understand how it works. So the most modern control system today will give you the option to have the SP, that is set point, track the PV when the control loop is placed in the manual. So what are the advantages of this type of controlling system? So its advantage is, since the SP is tracked the PV when in the manual, the value of the error at the time the operator flips the switch will be 0. As such, there will be no proportional bump at the time of switch. Now there is also some limitation of this control system. So which is that? So operator will have to remember what the normal SP should be for the control loop when it returns to automatic mode. And second one limitation is, by having the SP track the PV, the operator no longer has the SP gate at its normal value. And third one is, there could still be bump due to P action, that means proportional action, that create a bump if large change in SP is made after a transfer to the auto. So these are the advantages and disadvantages, or we can say limitation of the first one control system of the Bumpless Transfer. Now we discuss about the second one system of the controlling of the bump transfer, that means Bumpless Transfer. So here, suppress the proportional action at the instant that the switch from the manual to auto is made. So here we suppress the action of the proportional control. So you can see this is the transformation, how it works when we use this type of control system. Some modern control systems provide the option of suppressing the proportional action at the time of operation flip the switch from manual to auto. That means in the modern control system, there is the option is available of the suppress. So we can suppress the effect of the proportional that create the bump. We can suppress. So here, what is the advantage due to this controlling system? the SP remains at its nominal value during the period of time that the control loop is in the manual, thus preventing the operator from having to remember where the SP should be during the normal operation. Eliminate the proportional bound. So it can overcome the limitation of the last one system, control system limitation. So here this is the advantage for that. And now this system has also disadvantage. If there is an error present at the time of the operator flip the switch, it may take a considerable amount of time to drive the PV to the SP, since the proportional actions of the PID controller has been suppressed. So this is the main limitation of this system. That means if the error is present at the time of switching, that means from the automatic to manual or manual to automatic, so it may take a considerable amount of time to drive the PV to SP. That means it takes time to reduce the deviation. So because at that time we suppress the P controller, that is proportional action. So this is the limitation of this control system. So here we discuss about the advantage and disadvantage of second control system. Now in this lecture we discuss about the velocity and position algorithm of PID controller, and then we discuss about the Bumpless transform and how it works. So what is Bumpless transform we discuss, and how we can control this effect of a bump in the controlling system. That means we discuss about the two controlling systems. Thank you.